So far, we have only been reproving identities that we already had proved in a different way. Here is something that we have not done so far. This is an expansion of a product of two binomial coefficients with the same top elements. So here is a new identity. Let a and b be two non-negative integers and let x be a real number. Then the claim is that x choose a times x choose b is the sum from I equals 0 to a plus b. I choose a, h is a plus b minus I, x choose I. The meaning of this is that if you have a product of two binomial coefficients with the same x on the top, you can expand it into a sum of just single x choose i's. But it's not just a sum, it's a linear combination. It has those constant factors on the front. But still, that's pretty good. So it lets you expand the product of two binomial coefficients into like just sums of binomial coefficients. So how do we prove this? And again, this is double counting or bijection, depending on how you want to see it. I will show it as double counting. So first of all, we W log assume that x is a non-negative integer. Why? Well, for the same reason as before. Because if we can prove it, if we can prove the claim for all x, for all non-negative integers, then it will automatically follow, using the polynomial identity trick, that it also holds for all real numbers. Simply because on the left and on the right, you have polynomial functions at x. Okay, so now that we have assumed x to be a non-negative integer, we can go around interpreting things combinatorially. What is the left-hand side? So this counts a element subsets of the set 1, 2, ... x. And this counts b element subsets of the same set. So in total, this product counts the pairs of one of the first and one of the latter. So let x be the set bracket x, so 1, 2, ... x. And let us count the pairs a comma b, consisting of an a element subset a of x and a b element subset b of x. We count these pairs AB in two ways, as usual. And the first way is the left-hand side. The number of such pairs is x choose A, x choose B, because there are x choose A ways to choose A, and x choose B ways to choose B. So far, so boring. Now, let us get a way to count these pairs and get the right-hand side. This is trickier. But in a way, it's also painting my numbers. So because x choose I means you have to count, you have to construct an I element of x, and then an A element subset of the I. It's kind of reasonable to expect that this A element subset will be our capital A. So simply because there are not that many A element subsets around. So whatever I element subset we're choosing has to be between A and X. So, and just looking around, how could we find such a subset? We hit one possible idea. That could be the union of A union B, because A union B is a subset that contains A, but in turn is contained in X. This brings us to the following way of constructing such pairs. So here is a way to construct a pair A comma B consisting of an A element subset and a B element subset. First, we choose the size of their union. This size is an integer, so the size is an element of 0, 1, A plus B. I mean, actually, it is larger than it is larger or equal to A or to B, but it doesn't matter. So what is important is that it cannot be larger than A plus B, because the size of a union cannot be larger than the sum of the sizes of the parts. Okay, next, we choose the union itself. This must be an I element subset of X, so it can be chosen in X choose I many ways. Next, we choose the set A. This must be an A element subset of the union. So, and the union is, which is already fixed. So the union has, we don't need to choose it anymore. So it can be chosen in I choose A many ways. Okay, great. We have already explained these two factors and the summation sign. Now we need to make a last choice that will give us this many options. So finally, we choose the set B. So what does the set have to satisfy? So the set B must satisfy A union B is, well, A union B. I mean, A union B is basically chosen and A is chosen. And we're choosing a subset B that gives, if you take its union with A, it gives you the chosen union. And also it should be a B element set. So its size should be B. So this is a little bit awkward. It's not immediately clear how many such choices for B there are. So let me do it a little bit differently. Let me choose the intersection instead. This must be a subset of A. And furthermore, I claim that its size is I minus A minus, nope, it's A plus B minus I. Why? So that it's a subset that's clear. An intersection of A and B is always a subset of A. But what about the size? Well, for any two subsets A and where any two finite sets A and B, we have the size of the union plus the size of the intersection is the sum of the sizes. This is a nice and easy identity to check. Feel free to check it in your spare time, and we will also see how it follows from something much more general. But as a consequence, the size of the intersection is the sum of the sizes minus the size of the union. And in our situation, this yields the size of A is A, the size of B is B, and the size of the union is I, so this should be A plus B minus I. So A intersected B should be an A plus B minus I element subset of A. There are how many choices for this? Well, A choose A plus B minus I. Or options for choosing such a subset. Altogether, by the sum rule and the dependent product rule, we see, right, and I should say that having chosen A and A intersect B, we get B for free. As you can easily check, is that B is A union B without A, union A intersect B. This is basic set theory. You can draw the Venn diagrams and convince yourselves that they're the same. And I should, of course, say we also have chosen the union. So I'm leaving a few things unsaid here. In particular, I'm leaving it unsaid that if you choose A union B, A and A intersect B in this way, then this resulting set B will indeed be a B element subset, and its union with A will indeed be the union that we chose, and its intersection will indeed be the intersections that we chose. To be very strictly speaking, like this has to be proved, but it's all a matter of finite sets, so it's just like Venn diagram thinking. So we see that the number of ways to perform this construction is, so first we choose the size, and so everything else depends on the size, so we have to take the sum. Next we choose A union B, and we know already we have this many ways. Next we choose A in this many ways, and finally we choose A intersect B in this many ways. And so comparing the two results, we obtain X choose A, X choose B, equals the sum. And as I said, the identity is proved not just for non-negative integers, but also for all real numbers by the polynomial identity trick. And yes, you can, if you want to double check all these arguments, it's actually pretty helpful to draw the corresponding Venn diagrams. So this is X, there should be a circle for A, a circle for B. And so we begin by choosing the union. Having chosen that, we choose where the A lies, and then we also choose the intersection, and then the end B falls out of it.